Hello, this is Abhishek Gade and today we are going to learn about Joule Thomson coefficient. So see here you can see a pipe and then there is a restriction here. It can be anything, porous plug or an valve, an ordinary valve or a capillary tube, right? We want to do what is called as throttling. So enthalpy remains constant in throttling and throttling is an highly irreversible process. So see this is T1 and P1, temperature and pressure and inlet, and T2 and P2, temperature at exit. Remember, during throttling, pressure will always decrease. So P1 would be greater than P2. But what about the temperature? Will temperature increase, decrease, or remain constant? We don't know. That is the question mark. And here arrives the need of Joule Thomson coefficient. Do you know? See, practically, we have many applications. See, in refrigeration, there is something called as throttling, right? It is used for gas cooling. Okay, that refrigerant cooling is done, right? But do you think always cooling? No, sometimes it is heating also. So suppose like we have hydraulic oils moving through through pumps and pipes, right? Okay, so various pipes through them they are moving, and sometimes these pipes can be leaking and that could be a major challenge to find where they are leaking. So what happens is the place through where it is leaked, suppose it is leaked here, right, from here it is leaking, so throttling will take place, and because of throttling what will happen is there would be a warming effect produced and this could be sensed using thermocouple. So we can also take care whether we have leaking walls or not and change them, right, through this Joule Thomson effect. So one important application you learned right now. So not only for cooling, in heating also it helps. Okay, there are applications. Okay, so we'll move on, right? So Joule Thomson coefficient, right? So mu is equal to del T by del P constant H. Okay, constant enthalpy. Change in temperature upon change in pressure. Seems like this is something like slope, right? The temperature upon, oh yeah, it is something like, oh okay, so I will plot it. So this only the scientists did and they found that it was not like a same pattern. Okay, first it was, see, as we decrease the pressure, first it was increasing. Okay, the temperature was increasing and then it was decreasing, so a maxima was reached here. Okay, so suppose these are constant enthalpy line. Okay, this is a constant enthalpy line, so always when my pressure decreases I will move towards the left side. Let me start from here. I'm moving right, and yes, what happens, the pressure has decreased but the temperature has increased. What will be the Joule Thomson coefficient? Can you tell me? The Joule Thomson coefficient, when pressure decreases and temperature increases, it is less than 0. So two different things, it is less than 0. Just to remember, if you cannot. Then it reaches maxima, okay, and then again it starts falling. So if I start from this point, okay, my P1 and T1 are this point, and then I start throttling, so my pressure reduces as well as the temperature reduces. So both are in same direction, decreasing. That means Joule Thomson coefficient is greater than 0, right? This is going to help you to remember. Okay, same, both are decreasing. Okay, with decreasing pressure, if temperature is decreasing, then mu is greater than 0, right? But if different, if pressure decreases and temperature increases, then the Joule Thomson coefficient is less than 0. And in what case it will remain equal to 0, the Joule Thomson coefficient? Can you guess? Yeah, H1 equal to H2, CpT1 equal to CpT2. When it happens in case of an ideal gas, right? In case of an ideal gas, the Joule Thomson coefficient will be equal to 0. That means the temperature will remain constant, right? So for different enthalpy lines, this scientist plotted different enthalpy lines on TP diagram just to see what happens. So they found all were following some pattern. Okay, first they were increasing, then decreasing, same everywhere. So this maxima point, okay, what did they call them? They called them as the inversion point. Okay, inversion point, and this line passing through them is the inversion line, and the temperature here at this place is called as the inversion temperature. Why the word inversion? Can you guess? It is passing through zero slope. Okay, a zero slope or a zero Joule Thomson coefficient. It is passing through them. So why we call them as inversion? Because see, standing over this line, if we see on both the sides, both are having different pattern. Okay, the Joule Thomson coefficient is greater than zero at my left side. Okay, and greater than zero at my right side. Sorry, greater than zero at left side and less than zero at right side. So see, standing at one place, both the things are looking different. Okay, that's why this is called as inversion, because it is inverted, and these all are constant enthalpy lines. Remember, all are constant enthalpy lines, right? So yeah, but okay, what is this equation then? Okay, dH equals Cp dt plus V minus T del V by del T at constant pressure dP. This is a generalized equation for enthalpy. And we know for throttling process, this dH would be equal to 0 because enthalpy change is 0. H1 is equal to H2. And that means if I again want to get a desired relation for mu, I need to take dt by dp ratio. I just need to modify this equation and see what comes. Minus 1 upon Cp V minus T del V by del T at constant pressure. What does that equation mean? See, this equation you need to remember. Okay, what does that equation states? It states that the Joule Thomson coefficient, you can obtain it if you have the constant pressure specific heat. See this, if you have and you know the TVP relation, you can get del T by del P at constant H, that is mu. You can get it directly. Or else, if you want to find the constant pressure specific heat, you can do the inverted thing. Okay, reverse you can do. When you have PVT relations and data and all that, and you have Joule Thomson coefficient, okay, you can find Cp. So this was all about Joule Thomson coefficient. If you like this lecture, give a thumbs up as well as subscribe the channel for more updates. Thank you.